Okay, we were talking about Descartes' rule of signs, and this helps us find out how many positive and negative real zeros a polynomial function will have. So a sign change means if you put all your terms in order from the highest power of x down to the constant, a sign change is just as you go from one term to the next, does the sign change on the coefficient of whatever power of x that is. So here in this polynomial, your first term is positive, your second term is negative. So that is a sign change. It's going from positive to negative. As you go from the second term to the third term, there is no sign change because it's negative, negative. As you go from the third term to the fourth term, there is a sign change. You're going from negative to positive, so that's a sign change. Going from the fourth term to the fifth term, you go from positive to negative, so that's a sign change. And then from the fifth term to the constant, there's no sign change. It's just negative, negative. So this is how you count sign changes in a polynomial. And this may seem kind of crazy that can tell you anything about the zeros of the polynomial, at least it does to me. But this is something that is true that mathematicians back in the day figured out. They said, oh, look, this is what happens. So somehow they just, they were able to really, really put all their heart and soul into finding these patterns and figuring it out. So how do we use it? So here's what the rule says. Let f of x be a polynomial with real coefficients and a non-zero constant term. And we'll talk about how you deal with it if the constant term is not non-zero. If you don't have a constant term, we'll talk about that. It's pretty simple to deal with. But if this is the case, then the number of positive real zeros is either the same as the number of sign changes in f of x, or it is going to be less than the number of sign changes in f of x by a positive even integer. Strangely enough, this is true. That will tell you the number of positive real zeros that this function has. The number of negative real zeros is going to be the same as the number of sign changes in f of negative x, or less than that by a positive even integer. All right, so determine the number of possible positive and negative real zeros for this function. Okay, we've got it all in order from the highest power of x down to the constant. Now we'll count the sign changes. There's 1, 2, 3, 4, 5. There are 5 sign changes in f of x, which means that we will have 5, 3, or 1 positive real zeros. So 5, 3, or 1. Okay, so we've checked on the number of sign changes in f of x. Now we need to check on the number of sign changes in f of negative x. So I'm going to put in negative x everywhere I see an x into this function and see what I get. Well, if I put in negative x, I will get negative x to the fifth minus 6x to the fourth minus 12x cubed minus 12x squared minus 11x minus 6. No sign changes. No sign changes in f of negative x. So there are no negative real zeros. For this function. So positive, I can either have 5, 3, or 1. So it's the number of sign changes or less than the number of sign changes by a positive even integer, which is just 2 down and then another 2 down. So 5, 3, or 1. No negative real zeros, never, ever. The non-real zeros, if I have 5 positive real zeros, I will have 0 non-real zeros because the highest power in x here is 5. That means I'm going to have 5 zeros total. 5 total zeros. So no matter what, I'm always going to have 5 total zeros. If I have 3 positive real zeros and no negative real zeros, I must have 2 non-real zeros. It's got to add up to 5. If I have 1 positive real zero and no negative real zeros, which I'm not going to have, then I would have to have 4 non-real zeros to add up to 5. But it seems like in the book, they don't really care if they know every possible scenario. They just want you to tell them how many positive real zeros and how many negative real zeros for this kind of problem, where you're just showing how to use the law of signs. Okay, so let's look at this one. First of all, we know that we are going to have 6 total zeros because this is a degree 6 polynomial. The number of sign changes on the g of x, there are 2 sign changes as you go from the first term to the second term, and as you go from the third term to the fourth term, you have 2 sign changes. So since there are 2 sign changes on g of x, sorry, not f of x, there will be 2 positive real zeros or less than that by 2, which is 0. So there could be 2 or 0. So 2 or 0. Okay, now we have to look at g of negative x to see how many sign changes there are there. So g of negative x, if you go from the first to the second, you've got a sign change. So you've got sign change here, 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 and here. So 4 sign changes on g of negative x, so that means there will be 4, 2, or 0 negative real zeros. So the possibilities are, if you have 2 positive real zeros and 4 negative real zeros, that means you won't need any non-real zeros because you've already got 6. So that's one scenario. Another way could be if you have 2 positive real zeros and then you have 2 negative real zeros. Then you'd have to have 2 non-real zeros to make it all add up to 6. If you had 2 positive real zeros and no negative real zeros, then you'd have to have 4 non-real zeros. The other possibility with the positive real zeros is there could be none. So if there are 0 positive real zeros and 4 negative real zeros, you'd have to have 2 non-real zeros to add up to 6. If there were 0 positive real zeros and 2 negative real zeros, you'd have to have 4 non-real zeros to get 6. If there were 0 positives and 0 negative real zeros, you'd have to have 6 non-real zeros for that polynomial to have 6, as it should. Okay, I wanted to mention what you do if you don't have a constant term, because remember, to use Descartes' rule of signs, you have to have a constant term, and this polynomial right here does not have a constant term. So what you have to do is you have to factor out the lowest power of x so that what you have left over does have a constant term. So f of x equals x to the 5th times x squared minus 8x plus 15. So now you can quickly see that 5 of the zeros that this function has are 0. So that is a 0 of multiplicity 5. You put in 0 for x, you get 0. And so 0 is a 0 of multiplicity 5 for this function. And 0, since 0 is neither positive nor negative, that wouldn't be counted by Descartes' rule of signs. So that is a 0 of multiplicity 5. So there are 2 more zeros. And the question is, are they positive? Are they negative? Are they real? Are they not real? Whatever. So we're just going to look at this part of the function and see how many zeros just that part would have. So you can see that it has 2 sign changes from the first to the second and the second to the third terms. You've got sign changes. So it could have 2 positive real zeros here, or 0 positive real zeros. To figure out how many negative real zeros it has, we need to put in negative x for that. If we do that, we're going to have x squared plus 8x plus 15, which has no sign changes, so there would be no negative real zeros. So the only possibility is we could have 2 positive real zeros or 0 positive real zeros. 5 of the zeros are 0, and then the other 2 could either both be positive real or they could be non-real, because there are no negative real zeros. All right, the upper and lower bound theorem. First of all, a real number b is called an upper bound of the real zeros of a polynomial if all real zeros are less than or equal to b. So if you find a number that is an upper bound of the zeros, it just means that there are no zeros above that number. A real number is called a lower bound of the real zeros of a polynomial if all real zeros are greater than or equal to a. So if you find a number that is a lower bound, there won't be any zeros below that number. So if you kind of want to draw a picture of it, if you have an upper bound, there won't be any zeros above that value, whatever it is. And if you have a lower bound, there won't be any zeros below that bound down there. So that's what upper and lower bound mean. All right, so let f of x be a polynomial of degree n greater than or equal to 1 with real coefficients and a positive leading coefficient. So this is a condition that has to be true. You have to have a positive leading coefficient. And suppose that you are going to divide that polynomial by x minus c. So in other words, when you're trying to see if c is a zero of the polynomial, you'll do synthetic division with the number c in the little bracket. If c is positive, so it's greater than 0, and if both the remainder and the coefficients of the quotient are non-negative, then c is the upper bound. It's not the upper bound, it's a upper bound, okay? Because the upper bound, I mean, you could have an upper bound down here and you just don't know it yet. So the upper bound, just all it can tell you is there won't be any zeros above that. So it's not like you know it's definitively the upper bound. You just know there won't be any zeros above it. So it's an upper bound, an upper bound. All right, if c is less than 0, so if you've got a negative number in your little bracket when you do synthetic division, and the coefficients of the quotient and the remainder alternate in sign, with 0 being considered either positive or negative as needed, then c is a lower bound for the zeros of f of x. And again, this sounds so random and just crazy. Why does it matter what the signs on the coefficients of the quotient are? But this is how it is. Okay, example 9. Given f of x equals 2x to the 5th plus x to the 4th plus 9x squared minus 32x plus 20, determine if the upper bound theorem identifies 2 as an upper bound for the real zeros of f of x. So what we're going to do is divide this polynomial by x minus 2, which means put 2 in the bracket and put the coefficients of the function. Don't forget, there's no x cubed term, so you have to put a 0 there for that. And then do the synthetic division. Bring down the 2, multiply. 2 times 2 is 4. Add it up, 5. 5 times 2 is 10. Add it, you get 10. 10 times 2 is 20. Add it, you get 29. 29 times 2 is 58. Add it up, you get 26. 26 times 2 is 52, and you get 72. So we're just trying to see if 2 is an upper bound. That's part A. That's what they want to know. And so what does the upper and lower bound theorem say? It says that if c is greater than 0, so the number we're putting in the bracket is greater than 0, and if both the remainder and the coefficients of the quotient are non-negative, then c is an upper bound. So all these coefficients here, the 2, the 5, the 10, the 29, the 26, and the remainder are all non-negative. So they're not negative numbers. They could be 0, that's okay, none of them are, but they could be, but it just says they have to be non-negative. And so yes, 2 is an upper bound. Our c is greater than 0 and the remainder and coefficients are non-negative, so 2 is an upper bound for the zeros of f of x. So there won't be any zeros greater than 2. So when we list out all our zeros, all those p over q's, we don't have to include the ones that are greater than 2 because we know for a fact none of those will work. So that's what this upper bound theorem is telling us. All right, if we want to determine if the lower bound theorem identifies -2 as a lower bound. All right, so the way to do that is we put the -2 in the bracket and we do the synthetic division again. So we bring down the 2, multiply it, you get -4, add it up, you get -3 times -2 is 6. Add it up, you get 6 times -2 is 12. You get -3 multiplied by -2, that's 6. -32 minus 6, -32 plus 6 is -26. Multiply that by -2 and you get 52, and that is 72. So the lower bound theorem says if you're putting a negative number into that little bracket, the coefficients of the quotient and the remainder alternate in sign, with 0 being considered either positive or negative, depending on what you need, then c is a lower bound. So if you look, you can see that the signs on the coefficients do not alternate. They go positive, negative, positive, negative, negative, positive. So our C is less than 0. The remainder and coefficients do not alternate in sign. And so -2 is not a lower bound for the zeros of f of x. Okay, so we're going to use what we've done. We're going to use the tools we have to find the zeros and their multiplicities for this function. So we're going to use the rational zeros theorem to list all the possible zeros of this function. And remember, to do that, we are going to, first of all, we know there'll be 5 zeros because the highest power on x is 5. And then the possible zeros will be of the form p over q, where the numerator is going to be any factor of 20, the constant, and the denominator is going to be any factor of 2, the leading coefficient. So there are a whole bunch of possibilities there. We would have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20, and plus or minus 1/2, and plus or minus 5/2. So if you go through all the different combinations, 1 over 1, 1 over 2, 2 over 1, 2 over 2, 4 over 1, 4 over 2, 5 over 1, 5 over 2, 10 over 1, 10 over 2, and 20 over 1, 20 over 2. You get all these possibilities for the possible zeros. But if you notice, this is the exact same polynomial we were just working with. So let's jump back there and see what we already know about this polynomial. So first of all, we know that 2 is not a 0, and 2 is an upper bound for the zeros of f of x. So there will not be any zeros above 2. And we know that -2 is not a 0, and -2 is not a lower bound. So we don't know what the lower bound is. So anything, is fair game down there, but we know -2 is not a 0 anyway. We don't have to worry about that. But we know we don't need any of the numbers that are bigger than 2. So looking at that previous problem, we know that 2 is not a 0, and it is the upper bound for the zeros of f of x. So we can get rid of +2. We know that's not a 0. And we can get rid of all the numbers that are bigger than 2. So 4, 2, 4, 5, 10, and 5/2, all get rid of them. So we don't have to worry about those. Now, we know that -2 is not a lower bound because we tried it. But we could go ahead and try -4 and see if maybe that is a lower bound, and that would help us get rid of a bunch of other things. So we're going to try -4 as a candidate for either a 0 or a lower bound and see what happens. So we'll bring down our 2, multiply, you get -8, add it, you get -7, multiply 28, add it, multiply 28 by -4, you get -112, so you got -103, multiply that by -4, and you get +412, add that up, you get 380, multiply again, you get -1520, and that's -1500. All right, so we divided by a negative number, we put the negative number in the bracket, and our solution, the coefficients do alternate in sign down to the remainder, they do alternate in sign, positive, negative, positive, negative, positive, negative. That is the condition that tells us that yes, -4 is a lower bound. And that means that there will be no zeros below -4. We can get rid of -4 and all the numbers below it. So we got rid of all the numbers greater than 2, all the numbers less than or equal to -4 because we tried -4, it didn't work. We can eliminate 5/2 because, well, the positive 5/2 because that's greater than 2. Our only choices left are positive -1, positive and -1/2, and the possible -5/2. All right, we could then go ahead and use Descartes' rule of signs to see how many positive and negative zeros there will be. So if we go back up here to f of x and look at the signs, so that's 2 sign changes. 2 sign changes for f of x means you could have 2 positive real zeros or none. So f of -x, this will tell us how many negative real zeros there are. That has 1 sign change for f of -x. That means that there is 1 negative real zero. So we know there's definitely 1 negative real zero. Unfortunately, we have 3 to choose from, so we have to choose. And we know that there could be 2 positive real zeros or none. We'll try -5/2. And when we stick that in, bring down the 2, multiply it, you get -5, -4, 10, add it, -25, -16, 40, 8, 20, negative 20, and 0. So negative 5 halves is a 0. And if you remember, we just found out that there's one negative real 0 by using Descartes' rule of signs. So that's it, negative 5 halves. That's the only negative real 0 there is. So we know we've got x plus 5 halves for one factor. And then what do we have left over? We have 2x to the fourth minus 4x cubed plus 10x squared minus 16x plus 8. So now we know that the only possible zeros remaining, we used negative 5 halves, that's gone. We've got our negative real 0. The only things that we have left are plus 1 and plus 1/2. So we're going to take that big polynomial there, that 4th degree polynomial, and try 1 on that. So we'll plug 1 in there. We've got 2, negative 4, 10, negative 16, and 8. So we bring down the 2. 2 times 1 is 2. Negative 2 times 1 is negative 2. 8 times 1 is 8. Negative 8. And we get a 0. So 1 is a 0. So yay. So now we have x plus 5 halves for one factor, x minus 1 for another factor, and then what do we have left over? We have 2x cubed minus 2x squared plus 8x minus 8 for our f of x. Now, on the previous page, we found out that there have to be either 2 or 0 positive real zeros. Well, we just found one positive real 0, so there can't be 0, so there must be 2. So it means there must be one more positive real 0. So that could be 1 or 1/2. 1 could be a 0 of multiplicity 2, or 1/2 could be a 0. So we're going to have to take what we have left here and try 1 again. That would be easy. So we'll do that. We'll try 1 on that again. So we've got 2, negative 2, 8, and negative 8. So bring down the 2. 2 times 1 is 2. Get 0, 0, 8. And 8 and 1 is a 0 again. So we have the factors x plus 5 halves, x minus 1. That happens twice, so I'm going to put a square sign there. And then what we have left is 2x squared plus 8. So this is the factorization that we have. And so this quadratic right here, we can solve that with no problem. 2x squared plus 8 could be 0, which means that 2x squared would be negative 8, which means x squared would be negative 4. So x would be plus or minus 2i. So our zeros then are going to be negative 5 halves, 1 with a multiplicity of 2, and plus or minus 2i. So that's supposed to be 5 total zeros. So 1, and then 1 happens twice, and then you've got plus 2i and minus 2i, which makes a total of 5.